In this video, we want to look at estimating the mean when the standard deviation is unknown. In our last video, we looked at creating a confidence interval for the mean when we were given the standard deviation. And we said that was not very realistic. It was, working on your offense with no defense. So today we want to look at what happens when you don't know the standard deviation and some things change. But before we do that, let's go back and look at an example that we did already. The weight of Allen's hummingbirds are normally distributed with a standard deviation of 0.33 millimeters. A small group of 15 birds has been under study. The average weight for these birds is 3.5 grams. Find the 80% confidence interval for the average weights of the bird in this study, and what is the margin of error? So let's pause the video, and then let's see if you can find what the margin of error is, what the confidence interval is, and then give a brief interpretation of what that confidence interval means. So I'll let you pause the video. You can work this out, and then we can come back and we will go over the answers to review what we did yesterday to prepare us for what we're going to do next. All right, so let's look at where we're at here. So first off, our error formula is z sub c times sigma over the square root of n. So our z sub c for an 80% confidence interval, if we look at the chart in our formula sheet, that is 1.28. The sigma here is 0.33. We are dividing by the square root of 15. So my error is 0.109. To find our confidence intervals, we add and subtract our error to our x bar, which is 3.15. So if we add that, we get 3.041 between mu and 3.259. So there is our confidence interval for the average weight of the birds in this study. And I didn't circle it, but there is our error there. You always have to find the error before you can find the confidence interval. So how do we interpret this? Remember, we do not say there's a 80% chance that this confidence interval contains the mean. It either does or it doesn't, but we can say we are 80% confident. Let me say it this way. We are 80% confident that the interval from 3.04 to 3.26 grams contains the average weight of the Allen's hummingbird. So we want to make sure we say confidence, not probability or percentage or anything like that. So what we want to look at today when we don't know the standard deviation is we want to look at this new distribution. This distribution is called the student t distribution. This is very, very similar to our normal distribution, but it's a little bit different and has a little bit different shaped curves. And it's interesting why this is called the student t distribution and kind of how this came about and where this came from. This distribution was developed if you can't take large samples. If you can take a large sample, 100, 1,000, this is basically the same thing as normal that we've been looking at. But if you can't take a large sample and you need to take a small sample, they need a little bit different distribution, and that's where this came from. This is called student t because this was developed by somebody that worked in quality control at the Guinness Brewery. If you've heard of Guinness Brewery, it's a brewery beer out of Ireland, and this person developed this to do his product testing at the Guinness. Now, in doing this, he wanted to publish his results, but Guinness would not let him. They took it as a company secret, that they were the only ones that knew how to use this, and that gave them advantage over their competitors. So they told this employee that he could not publish this findings that he had come up with. Well, he decided to publish it anyway, but under a pseudonym, and just published it under the name Student. So they couldn't come back on him as being the one that invented it. Now, we've lost that person's name, or at least I don't know that person's name, but the name Student T has stuck. That's why this is called Student T distribution, because that first person that discovered it and wrote about it and developed it just published it under the name of Student because his company would not let him publish it because they thought it was a company secret. So what this is really going to do, we have a new formula for T. We're not going to really work with that much. But what we do need to change is this idea of degrees of freedom. So degrees of freedom are something that we use in the student T. And so the degrees of freedom, or another way to think about this, the sample size is going to change our critical value from what we did before. Now let me give you a way to think about the degrees of freedom. So let's for a second imagine that I have 5 colored blocks. This is maybe the best way to explain this so you understand it. So we have 5 colored blocks. And imagine if we asked 5 people to come up and take one of these. So the first person comes up and they choose the blue. So the blue's gone. The next person comes up and they choose the green. So the green's gone. The third person comes up and they choose the red. The fourth person comes up and they choose the purple. So of the first 4 people, they all got a choice. So there were 5 people. Now, if you're the 5th person and I say, you come up and choose a block, do you have a choice? Do you have any freedom of which one you can take? No. The first 4 had a choice. This 5th person has no choice. There is only one left. So if you have 5 people choosing, really only 4 of them have a degree of freedom. The 5th person gets whatever's left. So that's like an intuitive way of understanding the degrees of freedom. There's also an example we can talk about with numbers, but I think it's easier to think about people picking blocks or pens or whatever. And that last person gets no choice. You get whatever's left. So our degrees of freedom is going to always be n minus 1. Now, to find our critical value, we are going to call this a T sub C, not Z for our other confidence interval. We're going to be finding our T. And to do this, we are going to use our student T chart that is in our packet. So if you get out your formula sheet, your packet, this is the chart that is after the binomial distribution, but before the standard normal distribution. It is table 5. And we are looking at the top row. And across the top row, you will see the level of confidence, and you will see we don't have nearly as many that we can do here like we could with the other chart. We can either go 0.8, 0.9, 0.95, 0.98, or 0.99. That is it for student T. And then we're going to have our C is our level of confidence, just like before, and our N is the number in our sample. So in order to find this critical value, we need to know what our degrees of freedom is. So to go back to that formula, our degrees of freedom here is n minus 1. N minus 1 is our degrees of freedom. So here, if our n is 20, our degrees of freedom is 20 minus 1, which would be 19. So to find our T sub C, go to your chart. We are at 0.9. Go to 0.9, and on the left you can see it says DF, degrees of freedom, and you're going to go down to 19. We're not going to go to 20. We're going to go to 1 minus our n. So we go to 19, and we get 1.729. So that is our critical point for our student T distribution. So here, let's try a couple more. Find T sub C if our confidence interval is 98, with our sample size as 25, and then find our confidence level of 80, our sample size of 16, and find T sub C. I will pause here to let you find those 2 values from your chart. Okay. So across the top, we go to 0.98. Our sample size is 25, so our degrees of freedom is 24. So we go across to 24, we go to 0.98, and our degrees of freedom we get 2.492. For 80, we go to 80. Our degrees of freedom is 15, so we get 1.341. So really, that's the big difference from what we did yesterday, how we find our critical value. Because once we find the critical value with our student t, we have the exact same error formula. I'll go back to that in a second. We have the exact same error formula. We just have a t sub c, it's the student t, and we also have s instead of sigma, because we don't know sigma. We don't know the standard deviation, so we're going to use the mean and standard deviation from our sample to create our margin of error. Now let me go back to the part I had a second ago. If you look at your chart again, you will notice at the top, your critical values are much bigger, and as you go down the chart, they decrease. And you'll notice all the way at the bottom where it says infinity, those values at the bottom, if you would flip the page, are the exact same values that were on the standard normal chart. So as your sample size gets bigger, as your sample size increases, your t sub c basically increase to your z sub c. That's why student t is really useful for small sample sizes. It increases our critical value. And you can see it starts at 1 and it goes all the way up to 40, and then it jumps a few spots and then to 100 and 500 and 1,000. So if we ever have a sample size that's not on the chart exactly, let's say I gave you a sample size of 42. Your degrees of freedom would be 41. There is no 41 on the chart. You would just pick whatever's closest. So in our case, our T sub C would be based on 40 because we don't have that number. And as your sample size gets really big, it's basically the same as normal, so you're okay. Now, what this actually does, student T, if we look at it more closely, here you can see these graphs based on the degrees of freedom. So you can see as your degrees of freedom are smaller, basically what you do is you get more area out here in the tails. The black line is our normal curve where degrees of freedom's infinity. You get more area on the outside because you have a small sample. So that changes our confidence interval. It changes our distribution a little bit. So let's look at an example. Should go back maybe to the formulas. They're pretty much the same as yesterday, not much different from what we did before, adding and subtracting our error, just our new error formula. So, a company has a new process for manufacturing large artificial sapphires. In a trial run, 17 sapphires are produced. The mean weight for these is 6.75 with a sample standard deviation of 0.33. Let mu be the mean weight for the distribution of all sapphires. Find a 95% confidence interval for mu. So, our error formula is T sub C S over the square root of n. Now, our number is 17, so my degrees of freedom is 16. Our C is 0.95. So the first thing we have to do is we need to find our T sub C from the chart. So we go to 0.95, we go down to 16, and we get 2.120. So to find our error, we have 2.120, 0.33 divided by the square root of n. Be careful you still use n. Sometimes people get confused with degrees of freedom and n. We still use n in our error formula, and we get 1697. Now, our x bar, our mean, was 6.75. So to find our mu, we're going to add and subtract that, so we get 6.58 to 6.92. So you can see this confidence interval, and if we wanted to write the sentence, we can say we are 95% confident that the true mean of the sapphires is between 6.58 and 6.92. So you can see, compared to what we did yesterday, two things are really different. Our error formula is a little different. We have S. And the big thing different is how we get our critical value, how we get this T sub C. All right, you are now ready to do the homework on 6.